Hello everyone. The title of this video is Understanding Compound Inequalities. Now, each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 2.7, titled Linear Inequalities and Absolute Value Inequalities. And I'm working under the heading Understanding Compound Inequalities. Alright, so each example I'm going to be doing is either going to be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of this section that's related to this particular objective. And I would ask that when I start a new example, pause the video and try to work it out yourself first before watching me do it and comparing. Right? Because I feel that you should be practicing these things on your own, right, instead of just watching me do it. Right? Okay. Alright, so each example I have written out on paper. So we're asked to do two things for each example. We're asked to solve the compound inequality and then write your answer, right? Express the solution set using interval notation, which has been brought up in previous videos of mine, if you've been watching, or if you've read through section 2.7 of this algebra and trigonometry text at openstacks.org. Earlier in the section, interval notation is discussed. So I'm going to assume that you know what interval notation is. Alright, so before I get into my first example here, let's talk about these off to the side. Compound inequalities. Alright, so these are two or more, but usually we'll just consider two. Two or more inequalities connected by either the word and, by the words, and, or the word or. Right? Now, these are very different connecting words. In an and inequality, when two inequalities are connected by the word and, a number is only considered a solution of the compound inequality if it satisfies both inequalities at the same time. Right? So a number is a solution if a compound inequality is, has and as a connecting word. A number is a solution only if both inequalities are satisfied. Only if both inequalities are, made to be true. Right, so the and connector is very restrictive. Now the or connector is much more inclusive, is much less restrictive. If you have two inequalities connected by the word or, and we're only going to see one example of this at the end of the video, because this is a very simple case. It's the and inequalities that tend to throw people off. But if two inequalities are connected by the word or, a number will be a solution if it satisfies at least one of the inequalities, one or the other, or both. All right, this is called, this will be the inclusive, they call this the inclusive OR. So for OR inequalities, a number is a solution of the compound inequality if at least one of the inequalities is satisfied. Right, so not both, right? With and, it has to be both. Okay, so that's all you really need to know. Right? And then also, of course, you need to know how to solve a linear inequality. Right? All these inequalities we're going to come across in this video are linear. The highest power of the variable that you're seeing is the first power. All right. Actually, I guess one more thing I should point out before we get into example one is, see how example one, it's a statement with, two inequality symbols in it, a connected inequality, two inequalities joined at this middle part, this 2x minus 8. These kinds of inequalities are always and inequalities. So, A is less than B is less than C, or less than or equal to, is equivalent to saying that A is less than B and B is less than C at the same time. This is also very important for our purposes in this video. And it goes the other way around as well. If you see A is less than B and B is less than C, you can connect those like this. A is less than B is less than C. All right, but the word or will not show up. Right? These inequalities are only for and inequalities, and only for certain ones. Only where betweenness happens, right? This inequality here, when I say A is less than B and B is less than C, you could also say that B, right, the one in the middle, is, between A and C. Right? So yeah, this kind of inequality only really shows up when you actually are between two numbers, right? And it's always an and inequality. All right. So let me show you how we're dealing with these. So we're asked to solve this, compound inequality. Remember how to solve anything, right? You're trying to find the values you can replace the variable with to make a true statement. Find the values of x that make this expression here in the middle, the 2x minus 8, a number that's between 4 and 10, not including 4, but possibly including 10, right? Because you got less than or equal to 10. All right. So remember this statement here, this is equivalent to saying that 4 is less than 2x minus 8 and 2x minus 8 is less than or equal to 10. Right, it's two inequalities put together. Right. All right, so what we're going to do is we're going to solve each of these. Right, solve each of these, and then we're going to look for the numbers that satisfy both, because it's an and inequality. All right, so for this one, first step I'd be adding 8 to both sides. All right, so now we have 12 on the left is less than 2x on the right. And then I would divide both sides by positive 2 to get the variable alone. And you might recall the properties of inequality from my last video on solving an inequality in one variable algebraically. But when you divide both sides or multiply both sides by the same positive number, the inequality symbol doesn't flip. So I got positive 6 on the left and then x on the right. So 6 is less than x. Or if you switch sides here, that would be x is greater than 6. Remember, switching sides changes the symbol around. Alright, so here are the numbers that satisfy the first inequality. Alright, what am I going to do down here? So here's a number line. Alright, this is going to be a little number line. There's 6. Right, there's 6. And in one color, I'm going to put all the numbers that satisfy the first inequality. Right, the numbers greater than 6, but not 6 itself. Right, so notice the open point below 6 here, but all the numbers to the right of 6. Right, these satisfy the first inequality. Right, these satisfy, sorry about the tininess, satisfy the left inequality, I'll say. Satisfy the left inequality. All right, now what about the right inequality, or the second inequality? So pretty much the same steps. I'd be adding 8 to both sides first. Right, that gives me 2x on the left is less than or equal to 18 on the right. And then I'd be dividing both sides by positive 2, and again this is a positive number, so the inequality will not change direction. We'll have x is less than or equal to 9. Alright, and then I'm going to put in a different color these numbers, right? All the numbers that satisfy the second inequality, the numbers less than or equal to 9. Right, so 9 would be to the right of 6, right, on the number line. Then all the numbers less than or equal to 9 are these numbers. Right, less than 9, equal to 9, right? These numbers satisfy the second inequality, right? Satisfy the right inequality. Sorry about the tininess of that. But remember what I said over here, right? These AND inequalities, a number is only considered a solution if both inequalities are satisfied. So we're looking for overlap. Looking for overlap. What's called the intersection of these two sets. You have the set of numbers greater than 6 and this set of numbers less than or equal to 9. Where's the overlap? Where's the intersection? And that would be, these numbers here. Right, all these numbers here. Right? In the overlap. So this is not the graph that I'm going to finish with. Right? But I'm just pointing out the numbers that satisfy both. Right? So the graph I'm going to finish with, right, the final graph of the solutions of this compound inequality. I'll try to line things up. There's 0. Here's 6. Here's 9. Notice the only numbers that satisfy, both inequalities, the left one and the right one, are the numbers between 6 and 9. Right? The numbers between 6 and 9 are on both these graphs. Now how about 6? 6 is on this graph, right? There's a point 6. It's on the top one. It satisfies the right inequality. But notice there's a hole on the bottom one. So 6 satisfies the right inequality, but not the left one. 6 is not greater than 6, so 6 doesn't belong to the solution set, right? Open point. How about 9 though? 9 is on both. See, it's there and it's there. 9 is greater than 6. 9 is less than or equal to 9. So 9 actually is a solution. I put a point in it because it satisfies both inequalities. And then I leave it to you to check. Take any number between 6 and 9. Take 7, 8, 7.2, 6.3, 2 times pi, whatever. Take any number between 6 and 9, like 7. 7 is greater than 6, yes. 7 is less than or equal to 9, yes. Check more if you wish, but every single one of these numbers between 6 and 9 satisfies both inequalities. And then if you'd like, how about the numbers to the right of 9, like 10, 11, 12? Those don't satisfy both, right? They satisfy the left one, but not the right one. And the numbers less than 6, those satisfy the right one, but not the left one. Right? So the ones I've drawn here, and I'll put this in a box. This is the final graph, right? This is it. This is the picture of our solutions, the solutions of this compound inequality, the only numbers that satisfy both. Right? Now, another way to write this is that, x, the variable was x here, x can be any number between 6 and 9, right? See how we have betweenness here? Right? We have betweenness between two endpoints. So I can make one of those connected inequalities again, right? As I had up earlier, right? The only time you can make these connected inequalities is when there's betweenness. So x is between 6 and 9. 6 is not included, but 9 is, right? So I'm going to put the little or equal to under the inequality symbol by the 9. Right? And there's another way to describe the solutions, right, with an inequality. Right. Okay. Now they did ask also, to write the solutions in interval notation. Here I put up a graph, I put an inequality. These both describe the same set, right? All the numbers between 6 and 9, including 9 but not including 6. You can write it in words, you can write it in what's called set builder notation. I've done this in previous videos, but I'm just going to put up the interval now. They want the interval notation for this. Well, you always go low to high, left to right. The left end of this starts at 6, comma. The right end of the solution set ends at 9, right? And then on the ends, you put either parentheses or brackets, depending on whether or not the number belongs to the solution set. 6 is not a solution of the compound inequality, right? It satisfies the right inequality, but not the left one. So I put parentheses around 6. 9, right, the other end, is a solution, right? It does satisfy both. So bracket, right, one of these rectangular brackets on 9 to indicate that it does belong. And there you go. And this is what they wanted, right? This is the final thing they asked for, was write the solution set in interval notation. All the numbers from 6 to 9, including 9, but not including 6. Great. Okay, wonderful. All right, now just keep going. I'm going to do the same thing each time, for these and inequalities, right? For the and compound inequalities, you solve both of them. You look for the overlap, right? Are there numbers that satisfy both inequalities for these and ones? Then you make like a final picture, and if there's betweenness, you can make a connected inequality if you want, and write the interval. Yeah, and we'll see in the very last example has an or inequality. Or inequalities are very simple, I feel. All right, so let's do that again. All right, so the next example might be a little trickier, but not really. I mean, I'm still going to do the same stuff. Right? It's just that there's a variable, in all three parts of the it's another one of these connected inequalities. The last example, there was only a variable in the middle. But still, treat it the same. This connected inequality here, this is equivalent to saying the following, that 3y is less than 4 minus 5y, and don't forget and 4 minus 5y is less than 5 plus 3y. And then and it's just like the other example. So I'm going to solve both of these the way I normally would, a linear inequality. So on the left side here, I would personally, I personally like having the variables on the left side, but I'm going to add 5y to both sides. Now adding or subtracting doesn't change the symbol, so we have 8y on the left is less than, and then just 4 on the right. And then I would divide both sides by positive 8 to get the variable on the left alone, right? So we have y is less than 4/8 reduces to 1/2 or 0.5. Okay. So here are the numbers that satisfy the first inequality. Right? Y is a number less than 1/2. And again, what I'm going to do here is I didn't call it this last time, but I'll make a rough graph. Right? This is a first draft. So here's a number line, right? Here's 0, and then 1/2 is positive. Let's just put it to the right of 0. And all the numbers that satisfy the first inequality, the left one, are numbers less than 1/2, right? So not 1/2 itself, but just the numbers less than 1/2, right? So these satisfy the left inequality, right? The first one, I'll say, right? Whatever. Okay. And I do the same thing with the other one, and then we have this inequality. Alright, so for this one, I will subtract 3y, and get all the y terms on the left, why not? And I'll also subtract 4, right, to get all the constants on the right. So that's negative 8y now on the left. Still is less than, right? I was just adding or subtracting. And then 5 minus 4 is 1. And then I would divide both sides by negative 8. Right? And the symbol will flip. Don't forget that. Right? That tends to throw people off. Remember, when you multiply or divide both sides by the same negative number, the inequality changes direction. So now I have y, instead of is less than, is greater than, and then positive 1 divided by negative 8 would be negative 1/8. Right? So here's that'd be on the left side of 0. Here's negative 1/8. Right? That's to the left of 1/2 there. And all the numbers that satisfy the second inequality, this right one, are the numbers greater but not equal. And I'll put this below. Not equal to, so I have an open point there, negative 1/8, but all the numbers greater than, to the right of negative 1/8, right? So all the numbers I just drew here, right, these satisfy the right inequality, or the second inequality, whatever. And it's an and inequality. I am looking for the numbers that satisfy both at the same time. So I'm looking for overlap. Well, that's here. That's all these numbers between negative 1/8 and positive 1/2. And I'll use this picture to help me make a final graph of the actual solutions to this compound inequality. So the final, here again, here's 0, negative 1/8 and positive 1/2, and it looks like the only numbers that'll be on this final graph, the only numbers that satisfy both of these inequalities at the same time, are the numbers in between negative 1/8 and positive 1/2. But not negative 1/8 itself, right? Negative 1/8 is on the top graph, but not the bottom graph. So negative 1/8 satisfies the first inequality, but not the second one. So in the final graph, negative 1/8 doesn't belong, so that's why I'm putting an open point above it. And the same thing goes for a half. A half is not on the top graph. It's on the bottom graph, sure, but not on the top one. 1/2 doesn't satisfy the left inequality. Satisfies the right one, but not the left one. And remember, to be a solution of one of these and inequalities, you have to satisfy both. So I'm putting, again, an open point above 1/2. And there you go. Right, here's our final graph. All the values I can replace y with and make that original inequality a true statement. And you can check it out, test it out. Take any number between negative 1/8 or negative 0.125 and positive 0.5, positive half. Take any number between those two and plug them in for y back in the original, and it should be a true statement. And any other number, plug in a half, plug in negative 1/8, plug in anything greater than a half, plug in anything less than negative 1/8 for y, and this will be a false statement. Right. I'll leave it to you to test that out. Also, too, since our solutions are between two ends, we could, if we wanted to, write this inequality. Y, or the variable was y here. Y can be any number between, right, between these inequality symbols, less than, negative 1/8 and positive 1/2. Right, this is another way to say the same thing. Right, that y can be any of these numbers between negative 1/8 and positive 1/2. But they did want us to write, the interval notation for the solution set. So again, left end is at negative 1/8. The right end is at positive 1/2. And neither of those is included, right? So parentheses on both of them. Right. Great, and that's it. And I'll circle this. This is what they wanted from us at the end. The interval notation for the solution set. Right, but same stuff, same steps every time for these connected inequalities like this, right? Break it up to, the left inequality and the right inequality. You solve both of them, and then, it's an and inequality, so you're looking for the numbers that satisfy both at the same time. So you're looking for overlap on the graph to make a final graph, and then you can easily write the interval notation for the solution set. And if there is betweenness, right, if your solution set is a set of numbers between two endpoints, you can write a connected inequality again to describe those solutions. Right? But again, those connected inequalities are only when you have, betweenness, right, between two numbers. Cool. All right, example 3, same thing. Do the same stuff each time here, except for, again, number 5, my last example is going to be an OR inequality. All right, so once again, I have one of these connected inequalities, and this is equivalent to the left inequality, negative 4 is less than 3x plus 2, and the right inequality, 3x plus 2, is less than or equal to 18. Alright, so I'm not going to write out every little step this time. Alright, so I'm just going to tell you what I would do. First I'd subtract 2 and then divide by 3. So you'd have negative 6 divided by 3. That'd be negative 2 on the left side, and nothing would change the inequality symbol there, is less than x. Now, if you like having the variable on the left side, that would be x is greater than negative 2. Right? Switching sides changes the inequality around. So all the numbers greater than negative 2 are solutions of this first inequality. And again, I'm going to make a rough draft of a graph here first. Right, so here's 0, negative 2 would be to the left of 0. Alright, so all the numbers greater than negative 2 but not negative 2 satisfy the first inequality. Right? So there's the first inequality solutions. And 3x plus 2 is less than or equal to 18. I'd subtract 2 and get 16 over here. Right, 16, then divide by 3, you'd get x is less than or equal to 16 thirds, right, which is 5 1/3, or 5.3 repeating. Right? So that'd be over here, right, 16 thirds, and I'll put it on the bottom. So this is yeah. So x is less than or equal to 16 thirds. Less than would be the numbers left of it, right, or equal. So it is included. Right, so these are the solutions of the second inequality. And it's an and inequality, so we're looking for overlap, which are all these numbers, all these numbers here, right? All the numbers between -2 and positive 16 thirds. All these numbers are on both graphs, right? And so is 16 thirds, right? That's on both graphs. But -2 is not. -2 is on the second graph, but not on the first one. So it's not going to be on the final graph. So the final graph, right, with the solutions of this compound, this and inequality. So 0 there. And again, I'm just going to line things up. Right. So once again, the only numbers that satisfy both this and this are the numbers in between. 16 thirds does satisfy both, so it's a closed point. It is included in the solution set. -2 does not satisfy both, right? It satisfies the second one, but not the first one, so it doesn't belong. And then all the numbers outside this satisfy neither of them, right? So that's why they're not on the graph. Or satisfy one of them, but not the other, sorry. All these numbers to the right of 16 thirds, they're on the first graph, but not the second one, right? All the numbers to the left of -2, they're on the second graph, but not the first one. So again, that's why they're not on the final graph. All right, so here's the final graph. And once again, we have, betweenness. All the solutions are between two specific numbers. Now, if one of these went off to infinity, there's no betweenness. Right? Just be aware of that. Right? I actually have a dot and a dot. Right? If there was arrows, you're not between anything. So because there's betweenness here, I can write a compound inequality that's connected like this. Right? X can be any number between -2 and positive 16 thirds, not including -2, but including, right, so a little half equal sign there, the 16 thirds, right? And there's another way you can express the solution set as this connected inequality where x is between -2 and 16 thirds, not including 2, but including 16 thirds. And then the interval notation, for this solution set, it's going from -2 to positive 16 thirds, not including -2, right? So parentheses on that, but including 16 thirds, right? So bracket on that side. And there you go. That's what they wanted at the end, right? The interval notation for this. Great. And notice I'm doing the same thing for all of these, right? All these connected inequalities. Right? All these connected inequalities are and inequalities. All right, so I just got one more of these, right, and then we'll finally get to an or inequality. All right, so one more of these connected inequalities. So once again, these connected inequalities are equivalent to an and inequality. Left inequality of 3y is less than 5 minus 2y, and the right inequality, 5 minus 2y is less than 7 plus y. And again, I'm not going to write out every little step this time. I would add 2y, you get 5, y is less than 5, divide by 5, you have y is less than 1. Alright, so the numbers that satisfy this inequality are all the numbers less than 1. Okay. So I'll start making the rough graph. Right? So say here 0, say there's 1. Right? All the numbers less than 1, but not 1 itself. So open point above 1, there's all the numbers less than 1. Here's the solutions of the first inequality. Right, all the numbers that satisfy that left inequality. Alright, then over here, let's subtract y, get negative 3y on the left. Subtract 5, get positive 2 on the right. Divide by negative 3, so I'll change this from is less than to is greater than, and then you'd have 2 divided by negative 3, that'd be negative 2/3. Alright, so y needs to be greater than negative 2/3 there. Alright, so that would be here, somewhere to the left of 0 on the number line. And I'll put this in underneath. Now this is just the numbers, greater than but not equal to, right? So open point there, and then all the numbers to the right of negative 2/3. Now they don't always, they aren't, I promise you, they're not always going to be in the opposite directions like they've been for these 4 examples. They might go in the same direction. But just be aware that, this doesn't always happen. All right, now I'm looking for, since it's an and inequality, looking for the numbers that satisfy both at the same time, which again here are the numbers in the overlap, right? Between negative 2/3 and 1. Negative 2/3 is on the first graph, but not the second. So negative 2/3 is not a solution of this compound inequality. 1 is on the second graph, but not the first. Satisfies the second inequality, but not the first. So it is not going to be on the final graph either. Right? The only numbers that will be on the final graph are the ones between. Right? So the final graph is just composed of the numbers between negative 2/3 and positive 1, but not including negative 2/3, not including 1. Right, there you go. So there's the final graph, and once again, because there's betweenness, right, we're between 2 dots, 2 endpoints, we could also write, the variable is y. We say that the values of y that satisfy this compound inequality are the values of y between, negative 2/3 and positive 1, right? You could also write this to describe the solution set. And then finally for this, the interval, right? This is, left end at negative 2/3, comma, the right end at 1, and parentheses on both of those, right? Since neither one of those is a solution. Great. Okay. Now, the final example is totally different. Right? It's not a connected inequality anymore. It's an or inequality. Now, I brought this up, at the very beginning, at the very first page. When we have an or inequality, a number is a solution if at least one of the inequalities is satisfied. So that makes these very simple, in my opinion. Because all I need to do is solve one, and those numbers are solutions of the compound inequality because they satisfy the first one, right? They satisfy at least one of the inequalities. And then I solve the other one. And again, those are solutions of the compound inequality as well because they satisfy the second one. They satisfy at least one. And please understand that or inequalities can't be connected. Right? They can't look like all the inequalities we've seen. Right? This is a connected inequality, right? Like this and like this, a connected inequality. Or inequalities can, I'll make that note off to the side because that is a mistake I see made way too often. Or inequalities can't be connected like those and inequalities could when there was betweenness, right? So please understand this, right? Do not connect the solutions of or inequalities. Just leave the word or in the middle. Alright, so I solve each of these. Now in this one, I would add 5, giving me negative 6 over on the right, and then divide by positive 2. We'd have x is less than, negative 6 divided by 2 be negative 3. And, all the numbers less than negative 3 satisfy the first inequality. So these are solutions of the compound inequality. Or, here I would subtract 1 divided by 5. We'd have x is greater than or equal to 1. And all these numbers satisfy that second inequality. And because they satisfy at least one of them, they are also solutions. So there's no real rough graph I'm going to make here. Just doing a graph. We're not looking for overlap anymore, right? For OR inequalities, you just graph them. These numbers are solutions of the whole thing. These numbers are also solutions of the whole thing, right? OR inequalities are very, very loose, very inclusive. So here's 0, and then negative 3 would be to the left, positive 1 is mentioned, right? So positive 1 to the right. And, the numbers less than 3 are these numbers, right? But less than but not equal to negative 3, right? All these numbers satisfy the first inequality, so they're solutions of the compound inequality, the end, right? Or all the numbers greater than or equal to 1. Those are these numbers. And notice I'm putting them on the same level because, I'm not looking for overlap here. And this is it. Here are the solutions written out as an inequality with the word OR. Just leave the word OR in the middle. Again, do not connect them. There's no betweenness here, right? My solutions are not between two numbers. The only ones you can connect are with betweenness. And then here's the final graph. This is it. There's a picture of all our solutions. Every single one of these numbers will satisfy at least one of these. This one, or both. Right? Actually, none of them satisfy both, but and test it out. I leave it to you. But take any number less than negative 3, negative 3.1, negative 4, negative 5, plug them in for x, and you'll see the left inequality is satisfied. That's all you need. All you need is at least one of them to be satisfied for a number to be considered a solution to an OR inequality. And take the number 1 and any of these numbers, greater than 1, 1.3, 1.5, 2, 3, 4. They'll satisfy the right inequality. Right? So they'll satisfy the compound inequality, right? OR inequalities are very, very simple. And then negative 3 and all these numbers in between aren't solutions. They aren't on the graph. So test it out. Take any number between negative 3 and 1, like 0. 0 doesn't satisfy either of these. Right? So these numbers that aren't on the graph, they don't satisfy any of them. They don't satisfy either inequality. Right? But the other ones satisfy at least one. Right? Numbers that are solutions to these OR inequalities satisfy at least one of the inequalities. Is very, very loose, very, very inclusive. All right, now for the interval. And again, I'm assuming you've seen stuff about interval notation before, right? Now you see how there's a break in the graph? There's a gap between our solution sets, right? Parts of our solution set. That gap will be represented by the union symbol, which is another symbol. It's a symbol in set notation for the word OR. And again, you've probably seen this, but you got to go, again, go left to right, low to high. This first piece, there is no left end. So we go from negative infinity up until negative 3 is where that first piece stops. Parentheses on infinities always, and then parentheses on negative 3, because negative 3 is not a solution. It doesn't satisfy either of these. All right, and then with the gap, the break in the graph, got the union symbol. Right? I know I've put this up in a previous video on using interval notation, but this is called the union symbol. It represents the word OR in set notation, right? Or just a gap or a break in the graph on the number line. And then the second piece, just write another interval from left to right, low to high. It starts at 1 and then goes to positive infinity. 1 is a solution because it satisfies at least one of these. It satisfies the second one, right? So bracket on that, and then infinity, always parentheses. And here's your interval notation for the solution set to this compound inequality, right? But again, I'm only going to do one of these. The or inequalities should be much simpler than the and ones, right, I feel. Right. Great. All right, so pay attention. Right? Do you have the word or? Do you have the word and? Makes a huge difference, right? If it's one of those connected inequalities, it's an and one, right? And the or inequalities can't be connected. They shouldn't be, right? Great. Right, I'm hoping that watching me, go through these 5 examples here helps you in some way when you're asked to solve compound inequalities on your own. And thank you very much for watching.